Okay, so a little housekeeping and then back to lecture. We are hopefully, or you are, starting in on assignment 3, grad students 5 and 6. Just a note about assignment 3. In assignment 3, you're going to be implementing sensors for your robot. When you create your simulation and when you construct your robot inside the simulator, you can embed one or more sensors inside that robot. When you do and the simulation starts up, the simulation moves from one discrete time step to the next, which we'll talk about when we talk about physics engines on Thursday. At each time step, assuming your robot has some sensors, it is obtaining information from its environment. When the simulation ends, you collect that sensor data back, and PyroSim provides that sensor data for you. Some of what you'll be doing in this course is using that sensor data to assess the quality or the fitness of your robots. Those that obtain higher fitness survive, those with lower fitness die off. Usually we're computing the fitness of a robot as a function of its sensor values. So in assignment 3, as you implement, you embed your first sensor, which is a touch sensor in the white cylinder here. You're going to get information back from that touch sensor. At the moment, the touch sensor is just binary, so 1 will represent that object in which the sensor lives came in contact with the ground or another object, and a 0 represents that object did not collide with any objects during that time step. So you can view the sensor data as a raw vector. We are going to be using Matplotlib, which is a Python library for visualization. How many of you have used Matplotlib before? Some yes, some no, that's fine. If you have not used Matplotlib before, this might be a good time to go and Google a Matplotlib tutorial and work through some of those introductory exercises and familiarize yourself with Matplotlib, which will make things a lot easier for you in assignment 3 and subsequent assignments when we're doing some analysis of the sensor data. Okay, any questions about assignment 2, assignment 3? Grad students, you're on to 5 and 6. All good so far? Okay. We're working our way through the second theme of the course, where we're learning about the tools of the trade, the different elements we're bringing together to evolve our robots. We'll finish our discussion today on artificial neural networks. The field of neural networks is vast, and I touched on some aspects of neural networks last time. For our purposes, as I've already mentioned, we're going to be taking our artificial neural networks and putting them inside robots, so that when robots sense their environment, those sensor values are coming into the robot, and they're propagating through the neural network using neurons and synapses in the way we talked about last time. And the values that arrive at the output layer of the neural network, those values are treated as signals that we're going to be sending to the motors. Those are going to be turned into forces and torques, which we'll talk about in lecture 6. Basically commands to the motors which cause the robot to move. So based on how it senses, the neural network transforms perception into action. As we learned about when we talked about embodied cognition, the moment that the robot moves in its environment, its relation to the environment changes, which usually alters its perception, which means the values arriving at the neural network, at the input layer of the neural network change, which means the actions change. And we have this big feedback loop going from the input layer down to the output layer of the neural network, out to the robot's environment, through the environment, and back to the input layer via the environment. That feedback loop of action affecting the environment, causing change in the sensors, that's the embodied part for our purposes. Okay, so let's finish our discussion on neural networks, and then we'll move on to evolutionary algorithms. I finished last time again by touching on just some of the aspects of the vast field of neural networks. We introduced a number of elements of neural networks last time, the main building blocks, which are neurons and synapses. We connect neurons together with these arrows or synapses. Most synapses have weights associated with them. And the weight, or the W, which we'll use later on, is just a reminder that we're talking about the weight of influence of the source neuron, the neurons that's at the base of any one of these arrows, the influence of that source neuron on the target neuron. The larger, or the greater the magnitude of that synaptic weight, the further from 0 it is, the more influence the source neuron has on the target neuron, right? Negative synaptic weights are inhibitory, meaning they're pulling down or suppressing the value of the target neuron. Positive values are excitatory, meaning when the source neuron is firing more strongly or has a higher magnitude value, it's having a higher magnitude influence on the target neuron. Okay, so we have neurons, synapses, synaptic weights. We have values of the neurons themselves, which are obviously changing. We introduced activation functions last time, where we take the raw sum, or we compute the raw sum at any one neuron. Sometimes that goes beyond some desired value, and we squash that raw value back to lie within some desired value. For PyroSim, I think it's all neurons are between 0 and 1. It's been a while since I looked at it. The grad students that are a little further along, is it 0 and 1? Is it -1 to 1? Okay, it doesn't really matter for our purposes. We're squashing it to some desired value, so we have activation functions. And then, given those parameters, all of those weights, and in some cases those activation thresholds or activation functions, we can set them or change them, and by changing them, we change the function that the neural network embodies, right? We looked at this idea last time of how we could take a desired function, like a simple function, and, or XOR, and we could write down the weights and activation thresholds that would embody that function in that neural network. If we change the weights or change the activation functions, we change the function itself that the neural network computes. If there's something we want the neural network to do, what should those weights be? And hopefully from last time you took away that this is a pretty difficult thing to do by hand. You can do it for AND, you can do it for OR, you can do it for XOR if you really think about it. Beyond that, it gets very, very difficult to determine these weights by hand. So we want to automate this process. There's a lot of different algorithms out there to do that. One of the original ones, the backpropagation algorithm, people have been working on that for 30 years. They've got it to work pretty well now. Works very well when we have feed-forward connections. It says here it does not work for recurrent connections. It's a bit of an overstatement. There are versions of the backpropagation algorithm that can tune these synaptic weights even when we have these recurrent connections in them. But those backpropagation algorithms that work when we have these recurrent connections, they have to be very careful, because if you're not careful, you end up changing a lot of the weights in the neural network. And as you can imagine intuitively, if you're changing lots of the weights, you're changing the function by a large amount. And if you have a neural network that's already partially doing the job, it's partly optimized already, if you're making lots of changes, most of those changes are going to be negative, right? If you have a broken laptop and you hit it with a sledgehammer, you're unlikely to make it work better. So again, this course is not about backpropagation algorithm or learning algorithms in general. The point I want you to take away from these couple of slides is that it's a big challenge to make a small change to a neural network and have a small impact on its behavior. This, as you'll see many times in this course, becomes even more difficult when we drop these neural networks inside robots, because they have this embodied feedback loop. You can make a very, very small change to a weight, which will make a small change in the way the new robot reacts to its sensor value. But that slight change is going to propagate through the environment. It's going to move differently, which means the sensor values it gets at the next time step are different, which means its new actions are even more difficult. Because we have this feedback loop, it can amplify even small changes that we're making. It can amplify even small changes that we make to the neural network. So one of the big open challenges in robotics in general, and evolutionary robotics in particular, is we have a robot that's doing okay at what we want it to do. If you remember back to the beginning of the course, I showed you this simulated robot that picked up the blue block and was supposed to hold it on its back. Sometimes it fumbled the ball. So it's kind of doing the right thing. We want to make some very small changes to the robot's neural network, or possibly its body, to improve its behavior a little bit. That is exceedingly difficult to do, and we'll see some attempts to try and improve that as we go. Okay. Okay, so where does sort of evolutionary robotics fall inside the larger landscape of AI and machine learning? What we looked at in this lecture was actually what's known as supervised learning. Supervised learning is any task where we have certain amount of input, and we know exactly what sort of output we want from our neural network when we supply it with that input, right? The supervision is the M columns that you see on the right there. Given this input, I want you to do exactly this, right? That's supervised learning. Evolutionary robotics falls into semi-supervised learning, or you may have heard it referred to as reinforcement learning. In the case of our robot, when it senses 1, 0, we don't exactly know what action the robot should take. We know in general what we want the robot to do, which is possibly travel as far from possible as from its starting point. We place the robot at the origin, we give it a neural network, the robot senses something, which flows through the neural network to the motors, causes the robot to act, which changes its sensor values, it acts again, and we repeat this loop a number of times, in our case, inside the simulator. And at the end, we get back one number, which is how far the robot traveled from the origin. So it's semi-supervised because we can tell the robot, or actually we tell the evolutionary algorithm, which is evolving the robots, this robot did okay. It got 6.3 meters from the origin. Maybe there are other neural networks that will cause the robot to travel much further from the origin than that. We're giving back a little bit of a signal, but it's very difficult to take this global number, this one number, and go back and figure out where to tune the neural network to make the robot travel faster. If I go back a little bit to our discussion on backpropagation, in backpropagation, we have a supervised learning task. We know that we want the network to output 1, 0, and in this case, it's output 1, 1. So we know exactly where the error is, or at least the error is localized here. So we can go backwards, and we know that these synapses are to blame. These synapses are not to blame. We don't know that in a semi-supervised or reinforcement learning problem. Okay. Okay, that concludes our discussion about neural networks. I've only touched on some aspects of this vast field. Any questions about that before we switch gears and talk about evolutionary algorithms? Okay. All right, so we want to try and tune the synaptic weights for our robot. Most of the experiments we're going to see in this course, we're not going to worry so much about the activation functions. We're going to focus just on the synaptic weights. How do we do so if we're only getting back this one number? Well, there is another tool that's been out there for about as long as neural networks, which is a class of algorithms known as evolutionary algorithms. You may have heard of these before. The genetic algorithm is the most famous of these. We're going to look at a number of these evolutionary algorithms today, and we're going to start from the simplest ones and work up to more and more complex versions of this. They all share this basic idea, this basic underlying idea, which is, as a computer scientist, if you look at nature and you look at Darwinian evolution, you can boil down Darwinian evolution to an algorithm. You have a population of organisms. These organisms have very slight differences. Those slight differences cause some of them to survive long enough to produce offspring. And those offsprings are similar to, but not identical to, their parents. Those that have other differences, unfortunately, do not survive long enough to produce offspring. They're swept out of the population. And if we iterate through this algorithm long enough, you eventually obtain a population of organisms that are adapted to their environment. Obviously, evolution is much more complex than that. The devil is in the details. But the basic algorithm, which Darwin worked out in the 1800s, kind of intuitive, makes sense in retrospect. So, since about the 1970s, computer scientists have been borrowing this idea to try and automatically create solutions to problems. In our case, the problem is we'd like to get a robot to do X, and a candidate solution would be a set of synaptic weights for a neural network that, when placed in the robot, causes it to do X. Right? So in the genetic algorithm, or most of the evolutionary algorithms we're going to look at today, obviously we don't have a population of organisms. We have a population of data structures. In this little cartoon here, we have a series of vectors. Each one of these vectors contain a number of parameters that describe a potential solution to the problem. Some of these solutions may be better than others. Usually in an evolutionary algorithm, we're going to start with random solutions. We don't know what the weights in the neural network should be, so we create random weights to start. We don't just create one set of synaptic weights, we create n sets of synaptic weights. We take each neural network, one after the other, drop it into our robot, measure how far the robot travels, and that one number that comes back, we associate that one number with that one vector, and that's the fitness of that candidate solution. So imagine we have these random solutions here, and each one of these vectors now has a number associated with it, the fitness of that solution. Those with lower valued fitnesses are deleted, and those that survive, we make randomly modified copies of those vectors. What do I mean by randomly modified copies?
You introduce some noise into the neurons?
We introduce some noise to the synaptic weight values in these cases. We'll assume for the moment that these numbers represent synaptic weight, so we're going to introduce small random modifications. We don't, remember we're dealing with a semi-supervised task. Some of these robots travel faster and slower given these sets of synaptic weights, but we don't know which synapses caused the robot to slow down or speed up. So we're going to randomly modify a few of the weights by creating a new vector, like the middle vector you see on the right there, take that new set of synaptic weights, drop it into the robot, see how well that new robot does, assign a fitness to that new vector, and repeat this process eventually. We repeat this process. When do we stop?
When we stop seeing any improvement in our efficiency?
When we stop seeing any improvement, we could do that. When does Mother Nature stop? Never, right? So one of the nice things about evolutionary algorithms, which you've already probably figured out, is they're super simple. You'll see when you get on to assignments 7, 8, 9, and 10, you're going to be coding up some evolutionary algorithms. A lot of them take less than 10 lines of code. They're very, very simple to implement, but they have one limitation, which is we're never sure that we found the optimal solution. We may see that after a number of repetitions through this loop that there are no new robots that travel any faster than any robot we've seen so far. But that doesn't guarantee that if we go one more iteration through this loop, now we will discover a robot that travels faster than any we've seen so far. So an open question in evolutionary algorithms is when to terminate, and no one has a good answer to that yet. Question?
Is there any way to guard against finding like relative maximums for a certain value where there's like a dip and then like a small peak and then it would go way up, but you can't get to like the way up because it goes down first?
That's a great question. So you're talking about small peaks and mountains and hills and valleys. All that language you're using, we're going to introduce in a moment, and all that language comes from a metaphor from evolutionary biology known as the fitness landscape. And we'll talk about the fitness landscape in a moment, and then we'll be armed with the terminology to answer your question. Okay, so that's the genetic algorithm. It's been used since the 1970s. If you're ever stranded in an airport and you're waiting for a gate change and you don't know what's going on, blame a genetic algorithm. A lot of scheduling for flights in airports is done with not as simple a genetic algorithm as this, but an evolutionary algorithm. If you board the plane, and when you get on the plane, you look at the front nose cone of the plane, the actual shape of that for some of the aircraft, the shape of the nose cone of the plane was designed by a genetic algorithm. If the problem is to schedule planes into gates at an airport, these numbers might represent when did the flight come in, when is an airplane leaving, how far is the plane from the gate, and so on. So those numbers represent parameters that describe the problem about how to schedule planes at gates. If we're applying the genetic algorithm to design the front nose cone of a plane, what do you think the numbers represent in that case? Yes?
Drag or some other factor aerodynamic?
It could be. Drag is actually probably the number that comes back. Once we try out one of these candidate solutions, a nose cone in a wind tunnel or in a simulator, maybe drag is a number that comes back, and the greater the drag, the more likely that vector is to die, right? It could be the dimensions, size, curvature, volume, maybe materials. What do we actually make the nose cone out of? They describe sort of the building blocks of the problem. And then things like drag and lift and fuel efficiency, those would be numbers that would come back from any one of these candidate solutions when we simulate it or actually build it and try it out in a wind tunnel. And then those numbers would determine which of these candidate solutions survive and produce new nose cones which look like their parent nose cones, right? Yes?
You could have one algorithm that has multiple fitness outputs.
You, exactly. So in our case with our robots, we have one number, which is how far they travel from the origin. In the case of designing aircraft, there might be multiple numbers that come back that describe different aspects of the aerodynamics of that craft. We'll look at some evolutionary algorithms in a few weeks that are able to handle multiple fitness values simultaneously. Okay. The point I want to make here again is the genetic algorithm is not specific to any one problem. Scheduling, designing aircraft, designing robots, it's a general purpose tool. And in evolutionary robotics, as the name implies, we're going to apply an evolutionary algorithm to designing robots. So in our case, our candidate solutions, these vectors, for our purposes, we can now think of them as a population of robots. In a lot of these cases, the robot is just a set of synaptic weights that we're going to assign to the synapses inside the robot. But basically, we have a population of robots. We're going to simulate one robot after another, which you'll be doing in a few weeks' time. Here's one evolved neural network in a simulated robot. We're going to throw away the robots that do not do very well and make randomly modified copies of the robots that do well. You may not think it, but this is actually a robot that's doing relatively well at a particular task, which is known as brachiation. Brachiation is the fancy word for primates that are able to swing from limb to limb. This one isn't doing a great job at brachiation, but not bad. What else can you tell me about this evolved candidate solution? Think about our discussion about embodied cognition last week. How did evolution solve this problem?
Exploiting pendulum physics.
It's exploiting pendulum physics. So these little white rectangular solids that you see at the bottom, these are the two battery packs that are going to power the physical robot that you see on the right. If you've ever picked up an actual battery, it's pretty heavy. We put it towards the bottom of the robot, and if you watch carefully, you'll notice that the lifting of the hand and the placing of the hand is timed to the swing of the battery pack. So as the battery pack swings forward, temporarily the entire weight of the robot is lessened because the battery pack is rotating upwards. And when its weight is lessened, it's easier for it to lift its arm and place it a little bit further along the bar. Question?
For that body given to the computer, or did it dissolve, or did it evolve that?
We gave it this design, and it evolved a set of synaptic weights that produces the motion that exploits this body. As we move further through the course, we're going to see more and more experiments where we're also allowing parts of the body to be controlled by evolution. Descartes taught us 300 years ago that the body is sort of this thing that's holding down the soul. It's always in the way. I don't know if it's real. It's always a problem. Evolution obviously has a very different view of the body. It's a tool that can be exploited, right? We'll look again in a few weeks' time at attempts to take evolved solutions from simulation and transfer them to reality. It turns out that in practice, this is usually very difficult. We got lucky in this particular experiment that we carried out a number of years ago, where we actually were able to take this set of synaptic weights that you saw on the left, put it in the physical robot, and not only does it move more or less as it did in simulation, but the physical robot is exploiting the physical weight of the battery in the way that the virtual robot was exploiting the virtual weight of the virtual battery. This is known as crossing the reality gap. Usually when you take an evolved solution and transfer it from simulation to reality, it doesn't work. Why not?
Different physics?
Different physics, right? So those of you that have pushed ahead with the assignments, you probably figured out pretty quickly that Open Dynamics Engine, or ODE, which is the physics engine inside of PyroSim, it approximates real physics, but it does not emulate them perfectly. Right? Evolution is an exploiter. She will exploit anything that's given to her, like battery packs. She will also exploit inaccuracies of the physics engine. There was a question last week about your scissor bot, which should exist in the XZ plane, but after a while the YZ plane, but eventually it falls over to one side or the other because of the finite accuracy of floating point values. Right? Okay, something to keep in mind, which you will definitely see when you push forward with your assignments. Okay. All right, I mentioned briefly this idea of the fitness landscape. We're going to talk about this for a little bit. This is a central metaphor in evolutionary biology. It's been around since the 1930s. The fitness landscape is just a metaphor. It's not a real landscape, but it is extremely powerful formalism for thinking about what an evolutionary process does, regardless of whether we're talking about natural biology or artificial biology or artificial evolution like we're going to be using in this class. Okay, so what is a fitness landscape? Imagine we have a fitness landscape, and let's start simple. Let's start with a two-dimensional landscape. The horizontal axis is going to be every possible value for one gene. Let's imagine we have a very simple robot, like your scissor bot. We've got the white cylinder and the red cylinder. Last week, you attached the two cylinders together with a joint. This week, you're going to be placing a touch sensor inside of the white cylinder. You will, a little bit later, be creating a motor neuron. Finally, you're going to be connecting the sensor neuron to the motor neuron with one synapse, so that whenever this touch sensor fires, it sends a signal to the motor, and the motor applies a force to the joint, not unlike my muscles causing my forearm and upper arm to rotate relative to one another thanks to my muscles. Okay, so we have a very simple robot, two objects, one joint, two neurons, a sensor neuron and a motor neuron, and one synapse with one synaptic weight. If I want to alter the behavior of this simple robot, I can alter this single number, and it will alter the way that the joint rotates relative to what the touch sensor is sensing. So far, so good? Okay, if I want the scissor bot to scissor forward into the YZ plane, what value of W should I have? You can, again, when you get there, you can try it out yourself by setting it manually. Even in this case, where you have a very simple robot, it's hard to figure out what that value of W should be. Let's assume, for our purposes, that W can range between 0 at the center of the horizontal axis here, to -1 over here, to +1 over here. We're dealing with floating point values, so there aren't an infinite number of values we can set W to, but more or less there are an infinite number of values between -1 and 1 that we can set. Let's say we pick one of those values. So we're at some horizontal position in the fitness landscape. We set W to that value, we start up PyroSim, and our scissor bot doesn't move forward, it falls over. We get a value pretty close to 0 of traveling away from the origin. That would be a low fitness value. If we assign a different value for W, and the scissor bot actually manages to take 3 or 4 steps forward into the YZ plane, it gets a value of 3 or 4. We assign that value to that W, and that value, that fitness, is our vertical axis here. So if you think of every possible value of W, there's an associated fitness value. As you can also imagine, values of W that are very close to one another, generally speaking, cause the robot to do similar things, which give back similar fitness values for those two similar W values, which means any two horizontal positions in the fitness landscape have similar heights. Not always true, but most of the time. So if we were to then take all of those W fitness pairs and connect them together with a line, you would get this surface in 2 dimensions. So far, so good? Okay, so that's pretty easy to see. There was a mention before about hills and mountains. You can see in my little cartoon here, I've got 2 hills and 1 central mountain. So here, a value of W that's just a little bit greater than 0 would cause our scissorbot to travel as fast as possible. Negative values, it turns out that there is a negative value that gets the scissorbot to travel at medium speed, but more negative or a little bit more positive for that W, and it gets worse in either direction. Same thing here. A little bit more positive or a little bit more negative, the robot gets worse. So if we happen to find a value of W here where we have our scissorbot traveling at medium speed, we think we're doing well, and we try and modify that value of W, we're trapped, right? Any modification, any slight modification to W, and we get a slower moving scissorbot. In our case, again, we don't know what the landscape looks like. We know it exists, but before we try out anything in the simulator, that plot is empty, right? So how do we actually change W to eventually find, not only not get trapped on these hills, but land on the slope of the mountain and climb to the top of the mountain?
Increase the step size.
We could increase the step size, that's possible. So we could be, for example, sitting here, and instead of making small changes to W, we're going to make big changes to W. So we change W from this to this, then we change W from this to this, then from this to this, this to this. So just making the value bigger doesn't necessarily help because we're bouncing around quite a bit.
Would adding in some like major selection events help?
Maybe we could add in some major selection events. So maybe if we've been bouncing around for a little while and not making any improvement, we send in a simulated meteor and knock out 99% of the population and try again.
Maybe decrease the fitness cutoff to have some more tolerance for it getting worse.
Possibly. So we could, if we produce a new robot and it travels slower than the parent, maybe we keep that worse individual around for a little while with the hopes that the grandchild, the child of the child, will do better than either the parent or the grandparent. So maybe we're a little bit softer in our selection pressure. Maybe we could have 2 hill climbers. Why do we need to have just one? Maybe we could have multiple ones. There are hundreds and hundreds of things that you can do, or thousands of things. As I mentioned, the evolutionary algorithm has been around since the 1970s. Pretty much everything that you can think of has already been tried, but there are some things that also have not been tried. And again, we can look at nature. Biological evolution is much, much more complex than the little cartoon algorithm I sketched for you here. Maybe we can borrow ideas from biological evolution and build them into our artificial evolutionary algorithm.
What are some of the specific ways that it's way more complex than just the fittest survive?
Good question. All right, let's push on then and look at a little bit more sophisticated algorithms. We just introduced this idea of our fitness landscape where the horizontal dimension is 1 gene, but of course for more complex robots and for more complex organisms, we have more than 1 gene. Imagine we add in another touch sensor in the red cylinder. We add in another motor neuron here. So now we have 4 neurons and 2 synapses, and this motor is also contributing a value here. Now we have W1 and W2. Now our fitness landscape is a 3-dimensional volume, and we have a 2-dimensional surface. So we have 2 horizontal dimensions here, and any point in that horizontal plane corresponds to a single value for W1 and a single value for W2. And again, our third dimension, the vertical dimension, is fitness. For the robots you're going to be building later in the course, you're going to have 20, 30, 40, 50, 100 synapses. If you have 100 synapses, what is the dimension of your fitness landscape? 101, which obviously I cannot draw for you. So as I mentioned, the fitness landscape from this point onward is going to be a metaphor, and we might do some work with it formally. Here's the end of my geometric interpretation of the fitness landscape. As you can imagine, the fitness landscape is huge for most problems. It's already, assuming that genes take on floating point values, it's already almost an infinite space already. We might have arbitrary values for our weights, and there may be 100 of those weights. So we may have 101 dimensional space, and that space is vast, and we don't know what the surface looks like in that large space. We want to try and come up with an algorithm that can efficiently search the space to find not only these local peaks or these hills, but the highest point, which is, again, exceedingly difficult. All right, so let's start with the simplest evolutionary algorithm. It's not really even an evolutionary algorithm. I'm gonna leave this cartoon up here on the left. This is sort of the basic algorithm that's going to underlie all of our evolutionary algorithms. We usually start by initializing a population of solutions. In our simple Hillclimber, our population size is 1. We create one random candidate solution. We score the fitness or the quality of each individual in the population. We select those that survive and kill off those. We select those that have higher fitness, delete those that have lower fitness. I'm going to use the term selection for that. Variation, for the survivors, they're able to produce children that are variations on their own design. We repeat this process over and over again. We score the fitness of the new individuals we've just created, and we loop through this until some termination criteria is met, and we'll define what that is a little bit later. Okay, so in the case of the Hillclimber, we create one random parent, and let's assume for our purposes it lands on the slope of this hill here. We then create a randomly modified copy of that one parent, the child that you see down here. And in this case, the child got unlucky. It only differs in one number from the parent, but that caused the child to get a slightly lower fitness than the parent. What do we do with the child? Unfortunately. That's right. Delete the child, go back to the parent. The parent produces a second child. Let's assume in this case, the second child lands here. What do we do in this case? The child now has higher fitness than the parent. Keep the child, throw away the parent. The child becomes the new parent. That new parent produces a child. Rinse and repeat for as long as you like, right? Simplest possible, sorry, not the simplest algorithm. The very simplest algorithm is random search. Create a gazillion dots at random, evaluate the fitness of all of them. The one with the highest fitness, you're done. That's the simplest. This is one step up from random search.
Will we count for genetic drift and stuff, like the random killing off of?
That's a great question. So how do we deal with genetic drift? For those that aren't familiar with that concept, can you give us a summary of what genetic drift is?
I'm pretty sure it's just like you have a group of green and brown bugs, and a bunch of the green ones just get stepped on, then you're gonna have only brown bugs pretty much, because that brown bug population is a lot bigger than green. So then you're sort of removing that green gene from the pool.
Absolutely. So as you'll see in some of the algorithms here, genetic drift does exist. There are cases where mutations that might have been useful later on get removed from the population prematurely. And how do we know? What do we know? What do we keep and what do we throw away? In the case of the Hillclimber, it's pretty simple. We have two individuals. One is better than the other. Keep the better one. That's the Hillclimber. As you can see, obviously, in this cartoon, and you've already probably figured out, Hillclimber is simple, but it doesn't work very well. It's a weak, what's known as a weak learner, or for our purposes, a weak evolver. Simple to code up, takes about 5 lines of code. But you get easily trapped on what's actually known as local optima. So local optima is exactly the same as the hills that you see here. So within a local region of the space, like for example, this local region, this point here is optimal, but it's optimal only locally. Globally, this point is the best, right? So we'll talk about hills or local peaks or local optima. They all mean more or less the same thing. We're looking for the global optimum. There actually may be more than one if there's 2 equally tall mountains. That's what we're looking for. If we run our evolutionary algorithm for a while and we don't see any improvement, are we sitting at the top of a local optima, a hill, or are we sitting at the top of the mountain, the global optimum? Tricky. Okay. So, as has already been mentioned, if we now want to make a slightly more complicated algorithm that's a little bit stronger than the Hillclimber, Let's parallelize things. The heart of most evolutionary algorithms is that they're using a population of solutions at any one time, not a single individual. In all the videos I've shown you so far, we have sort of these snapshots of one robot after the other. At any one point where I take the snapshot, there are n-1 other robots that aren't in the video. Keep that in mind as we move forward. In all the experiments we're going to look at, we're usually looking at one evolved robot that's being drawn out of a population. So parallel Hillclimber, we create P parents. In this case, we'll just create two, P1 over here, P2 over here. At the at the variation stage, we take each parent, and each parent produces one and only one child. We score the fitness of each of the children, and we compare the child against its parent. If the child is better than the parent is deleted. If the parent has a higher fitness than the child, we delete the child, and we do that for each parent-child pair. How do you think the parallel Hillclimber does compared to the Hillclimber?
I think it does better. Does it do better? I guess I have a question.
Okay.
Does it do better for local optimum? Because then do you compare the populations of the children and then delete the populations with the less overall fitness value?
You could, but in the strict parallel Hillclimber, we're going to assume we always have a population size of n, and each n is a parent-child pair. So if a parent-child pair is doing worse than some other parent-child pair, we're never competing pairs against one another. They're all separate lineages doing their own thing, for now. I've obviously cooked this example to bias the answer. Does better than the simple Hillclimber, but if you have lots of local optima in your fitness landscape, in this case we only have two, in practice you have a very large number of local optima. The parallel Hillclimber doesn't help you too much because it tends to get trapped on a bunch of these local optima throughout the space. Often we're dealing with something that is almost a needle in the haystack problem. The haystack is the fitness landscape and the needle is the global optimum. Parallel Hillclimber helps, but it doesn't help too much. So let's keep going. We're going to look at a series of these algorithms that are getting more and more complex and getting a little bit more powerful in terms of biasing our chance of finding the global optimum. Okay, third one we're going to look at is the genetic algorithm. This is sort of the most famous of all the algorithms that are out there. We're going to start exactly as we did with the parallel Hillclimber. We're going to create n parents. When we get to the selection stage, we're not going to allow each parent to produce one child. We're going to look at the fitness of each parent in turn. And parents that have lower fitness are less likely to produce offspring, and parents with higher fitness are likely to produce more offspring. So we're going to introduce some probability here. So based on your fitness, that dictates how many children you produce. So at any one generation, the majority of parents are producing no children. A small minority are producing one child, and even smaller minority produce two children. Some produce 3, 4, 5, 6, 7. They might produce quite a few children. We've got a very large population now. Those new children replace the parents that produced no children.
So, I guess maybe two questions. Offspring size isn't usually dependent on the fitness of the parent, right? That's like a fixed value.
Again, within the class of genetic algorithms, there are lots of different variants. The one theme across all of them is that it's probabilistic. The higher your fitness, the more children you're likely to produce. There's different ways you can implement that. Did you have another question?
Yeah, so it doesn't do any probability. It's very possible that the most fit parents won't reproduce.
That can also happen. So just because we're doing things probabilistically, it may be that a really good parent produces no children. Or a parent that had low fitness might just get lucky and produce a child. Remember this issue where even though an individual may produce low fitness, it may be sitting low down in a valley, yet unbeknownst to us, it's sitting on the lower slopes of the global optimum, right? So the genetic algorithm is a little bit more forgiving in that it often will keep things around that don't necessarily have higher fitness. And depending on how we implement those probabilities, we can be more or less forgiving in that process. One other element that we tend to introduce in the genetic algorithm is recombination or crossover. So in the algorithms we've talked about so far, usually we're just randomly modifying the children by introducing a mutation. We travel along our parameters, pick one or a few of those parameters, and change them by a small amount. So we're simulating mutation. But of course, we may have, like in the cartoon that you see here, we may have parent 1 sitting on the slope of one local optima, and parent 2 sitting on the slope of a different local optima. What does that mean? It might mean that P1 has figured out one part of the problem, but not another part of the problem. Let's assume the problem is made up of two parts. Remember our discussion last week about the XOR function and how we built a neural network that computed and OR and then combined the results? We can continue that example here. Imagine P1 and P2 represent different sets of synaptic weights. In P1 has figured out how to create the AND function, but not the OR function yet. P2 has figured out how to create the OR function, but not the AND function yet. They're getting parts of the solution right, and they're getting different parts of the solution correct. Possibly, if we cut them in half and combine partial solutions together, if we get lucky in the two parents that we choose for crossover, and we get lucky at the point at which we cross them over, we may, in the children, bring together the best of both possible worlds. We may produce a child that correctly computes AND, like parent 1, and correctly computes OR, like parent 2, right? That's part of the reason why recombination evolved in nature in the first place. It's also a little more complicated than that, but the general intuition makes sense, right? If you've got a complex problem out there and you have a population of candidate solutions, they could be organisms or robots or airplane nose cones, some of the individuals in those populations may have figured out different parts of the problem, and we may be able to recombine them together. Turns out in practice that is notoriously difficult, and we'll come back to that issue later in the course. Okay, so in my little cartoon here we have two children. This child is inheriting the left part of the red parent. This child is inheriting the right part of the red parent, and vice versa. In the case of child 2 here, it got unlucky. We combined the worst of two possible worlds, and it ended up still trapped on a local optima. But in this case, we got very lucky, and in C1, we brought together the best of P1 and P2, and it's not at the top of the global optimum, but it's pretty close. We've got AND and OR, and maybe the weights that are combining those two subfunctions to compute XOR are close. Not quite there, but almost there. Maybe if C1 produces a grandchild, GC1, with a few more mutations, the grandchild or the great-great-grandchild may find the global optimum. So far, so good? Okay, so that's the genetic algorithm. It was mentioned before, one of the things that might help us here is to change the step size. So what do we mean by the step size? The step size for our purposes is going to be short for the amount of change we introduce from one child compared to the parent. Remember our discussion a few minutes ago about back propagation and tweezers versus sledgehammers. We want to try and make small changes to our solutions. But if we always are making small changes, we may be stuck on a slope and just gradually, slowly climbing a local optima. So there are cases where we want to make big jumps and cases where we want to make small jumps. How do we know which is which? There was another algorithm introduced called the evolution strategy. Again, it's like the genetic algorithm, but we add on an additional part here to a candidate solution. So we have our genes up here as usual. Here are all our synaptic weights. And we're going to associate with each of these synaptic weights a step size. And again, we don't know what those step sizes should be, so at our initialization phase, we're going to set them to random values. If this parent produces a child down here, and we pick the second gene to be mutated, its current value is 0.4, how much should we change that 0.4 value for? By? We'll change it by up to 0.6 or down to 0.2. So we'll modify 0.4 by plus or minus 0.2. It's got a relatively large step size. If, however, when we create the child, we choose the first gene for mutation, we're going to alter 0.3 by a smaller amount, a smaller step size. So each gene has a small instruction associated with it by how much we're going to vary it. Why would we do that? Well, let's have a look here. In the upper cartoon here, we have a relatively easy fitness landscape. What do I mean by easy? There are only a few local optima. There are 2 hills in this case and 1 global optimum. If we have a solution that is sitting here, we can assume, if we assume that this solution has a step size of 0.1, that means that its children may lie 0.1 to the right of it, or up to 0.1 to the right of it, or up to 0.1 to the left of it. So if we look at this region of the slope here, half of those solutions are going to be better. If they fall to the left of the parent, they're going to be better than the parent. But half of those potential children are going to be worse than the parent. 50-50, that's actually pretty good, right? However, in practice, fitness landscapes rarely look like this. They tend to be much more rugged. There tend to be much more local optima. What does that mean? What that means is that if we have any point in our fitness space and we move horizontally, even by a small amount, that small change to W, for example, which is moving us a small distance horizontally in the fitness landscape, can have potentially large impacts on fitness. It's very difficult to make any change, even small changes, and have a small impact on behavior. That makes things very problematic because, for example, if we exist at this point in the fitness landscape and we still have a step size of 0.1, now 99% of the candidate children are going to be worse than the parent, and only 1% are going to be better. So a step size of 0.1 doesn't work for this parent and this gene, gene 1, under these conditions. We would like to have a smaller step size. But again, how do we know? How do we set these step sizes, or as they're known for evolution strategies, the strategy parameters? What's the strategy of modifying the value of a given gene? How are we going to set these step sizes?
As it starts to converge, you lower the step size.
We could do that. So as it starts to converge, after we've done a large number of iterations, we've seen little or small improvements, maybe we start to make the step sizes smaller. We start with a sledgehammer. We start by making large step sizes and jumping around the fitness landscape. But as time goes on, we start to make smaller and smaller jumps. That's not a bad intuition, and that's also used in a related algorithm called simulated annealing, which we're not going to talk about in this course, but if you're interested in that, you can go and have a look. In simulated annealing, they do exactly what you just described. The horizontal jumps that are made by the search process get smaller and smaller over time.
Sort of what you said, but don't tie it to over time, but the change in fitness between parent and child.
You can tie it to the change of fitness between parent and child, right? So remember, we're setting these step sizes at random. If a parent produces a child and we modified, for example, gene 1, that means we modified gene 1 by 0.1. We used the strategy of 0.1, and we did better. We moved up the slope. So maybe we exist in this case. If a lot of the children produced by this parent do better than the parent, then 0.1 makes sense for that parent. We should keep that value. If down here we still have this parent and it has a strategy of 0.1, and we're modifying gene 1 by 0.1, and we produce 10, 20, 100 children from this parent, and they're all worse than the parent, then 0.1 probably doesn't make sense, and we would alter it. And we could either make it bigger or we could make it smaller.
How do you tell which?
How do you tell which? You tell me. You have a step size and you're mutating, you're producing children according to that strategy. The children aren't doing very well.
This would take a lot of time, but could you choose a step size, sample a bunch of children, see like what ratio is better to worse, and then alter the step size based on that ratio?
You could actually use the ratio to try and estimate the strategy itself. That's a great point. And there is yet another algorithm that does that. It's called CMAES. Evolution strategies, covariance matrix adaptation. It's a little bit more complex than the evolution strategy. Again, we're not going to talk about it in this class. It turns out that if you do some math, you can actually try and estimate these directly. But if you're feeling a little bit lazy and we aren't going to try and estimate these step sizes, and it turns out doing this is actually computationally intensive. Like you said, you need to produce a lot of children to estimate this ratio. What else could we do?
We just start making the step size smaller. You can only make it really so small, I imagine.
We could start to make it smaller by how much?
Yeah, that's true.
This is getting tedious to do by hand.
Could you use calculus, and so you set a step size, kind of calculate, I guess, the slope of the fitness function?
That's more or less what CMAES does.
Oh, wait, so would like a machine learning style cost function be the same kind of deal with the CMAES?
Possibly. Let's stick with this. Again, I'm feeling lazy this morning. What might we try?
Could you sample from some sort of distribution, like a normal distribution, and change the global standard deviation based on how everything's doing?
Maybe, again, so we could treat the strategy parameters as a mean or standard deviation, or maybe we introduce two strategy parameters, one which is the mean and one is the standard deviation. We could try and shrink or grow it.
If that's lazy, would be random search, just randomly.
We could randomly search those values. We could keep changing them at random. Okay. That's really lazy. That's okay. What else could we do?
I mean, if you know what direction you're going in, then you could logarithmically increase or decrease.
Maybe.
Can we get to the slope?
Why not evolve them? In this course, usually, when it's hard to do by hand, and we don't want to use something that's very computationally intensive, we're going to mutate and cross the step sizes themselves. Let them mutate. If you produce a child and the child survives, great. If the parent is producing children and they're not doing very well, start producing children from that parent and let the step sizes change. I don't know whether they should be bigger or smaller, so mutate them.
Could you get stuck in a local optimum for step size by doing that?
So there's a problem with the evolution strategy, which again is relatively simple. It's simpler than some more sophisticated things. We can get lazy and let evolution do it, but now we get into infinite regress, right? We're mutating the step size. How much do we mutate the step size by? Maybe we should have a step size for every step size, right? Gets tricky. Again, this isn't a course on evolutionary algorithms. Professor Epstein teaches a course on evolutionary algorithms where she goes into much greater depth on all of these different algorithms. Hopefully what you're taking away from this is this general trade-off between the complexity of the algorithm and the efficiency with which it can approach the global optimum. Okay, let's look at one last one. It says here symbolic regression. This is actually the problem that this evolutionary algorithm is going to solve. The name of this evolutionary algorithm is genetic programming. Genetic programming is similar to genetic algorithms with one important difference, which you can see here. In the genetic algorithm and the other evolutionary algorithms we've been looking at so far, we've been dealing with genomes which are vectors, right? Strings of numbers. In this case, the genotype or the genome is going to be a tree or possibly a forest, multiple trees. Before we talk about genetic programming, let's just pause for a moment and introduce some more terminology. Throughout this course, we're going to talk about genotype and phenotype. Genotype is the blueprint, the thing that evolution mutates and crosses. In this case, the genotype is a tree. In this case, the genotype is actually a 2 by n matrix for the evolutionary strategy. If you go further back, for the genetic algorithm, the genotype is a vector. So we've got different data structures which are encoding the genetic information of the candidate solution. That's the genotype. The phenotype is the thing that the genotype produces. If the genotype is the blueprint, then the phenotype is the thing you build from the blueprint, right? If the genotype encodes a bunch of curvatures and dimensions, that's the genotype. The phenotype might be the actual airplane nose cone we build from that set of curvatures and dimensions. The data structure we use for the genotype is different from the discussion we've been having so far, which is how to modify the data structure. Do we mutate it? Do we combine material from multiple genotypes? How much do we mutate things by? Those are questions about selection and variation. Here, we're changing the data structure of the genotype itself. Okay, so I'm going to introduce genetic programming to you here, and we're going to apply it to a particular problem, and that problem is called symbolic regression. So let's first of all, in symbolic regression, we're going to actually be evolving. The genotype is going to be encoding equations. So the genotype are trees that you see here, and the phenotype are going to be the equations that are encoded by these trees. You can actually read off the equations that are embedded in these trees by traveling depth first down to the leftmost leaf. We have 0.8 plus x. Put brackets around this whole thing. This whole thing is multiplied by 1.4. For those that haven't seen this before, this is known as infix notation. Not really important for our purposes. We're just using infix notation and symbolic regression to introduce this idea of genetic programming. Okay, so let's work through these 5 steps of genetic programming. We want to create a population of solutions. So in this case, we have a population size of 2. We have 2 parents, P1 and P2. We're creating these at random, and we're creating these trees at random using 2 bags that you see on the right. We have a bag that's filled with operations, trigonometric and algebraic operations. That's one bag. And in the other bag, we have possible terminal nodes or leaf nodes. We have variables, we have floating point values, and so on. So let's create a tree in genetic programming. We start with P1. It's empty for the moment. We have these 2 bags. We pick one bag at random. In this case, we chose the operations bag. We reach into that bag, and at random, we pull out one operation from that bag. In this case, it's plus. So we pull out multiplication. We place the multiplication operation at the root of the tree. Multiplication requires 2 arguments, A and B. So we create 2 edges going down to 2 empty subtrees. We go to the left subtree. We pick one of the 2 bags at random again. In this case, we pull out a plus. Plus requires 2 arguments. We go back down to the lower left of plus. We pick the terminal node bag. In this case, we pull out a random floating point value, which is 0.8. We filled in that part. We keep going until we filled in the rest of the tree, and we now have a random tree which encodes a random equation. We then go to P2, which at the moment is an empty tree. We play the same game of randomly combining operators and operands until we build a random tree that encodes a random equation. What random equation is encoded in P2? Let's test your infix reading ability.
0.2 divided by bracket x plus y.
0.2 divided by x plus y that you see here. Okay, so we have 2 trees that are producing these two equations. We have the genotype, the tree, and the phenotype, the equation. We haven't introduced fitness yet. What is the fitness of any one of these equations? We'll introduce that idea in a moment. Let's look at some of the variation operators. We have our 2 parents. We're skipping over fitness scoring and selection for just a moment. How do we vary these trees? Well, we can mutate these trees by picking a node at random, deleting that node, and then reaching into our bag of operators and operands again and building a new random subtree. That would be a mutation operator. Or we can introduce sexual recombination, where we take two parents, we pick two subtrees, one in each parent, the red subtree and the blue subtree, pull them off, and swap them. Right? So now we have child 1 and child 2, which are similar to their parents. C1 shares this term in common, and it shares this term in common with its second parent, and vice versa. So we have two child equations which are similar to but not identical to their parents. So we have genetic programming, and we're going to apply it to this problem of symbolic regression. Not that different from the other evolutionary algorithms we've seen. We have candidate solutions, which in this case are these equations. What are these equations supposed to be doing? Okay. There are a lot of problems in math, in science and engineering, where we would like to come up with an equation that describes some observed data. So let's look at some cartoon data here. Let's assume that I can make a number of observations of two variables, x and y, and I want to know how these two variables are related. I can pick different values for x, which is my dependent variable, and for each value of x that I pick, I send it to the system that I'm trying to understand, and the system gives me back a value of y associated with that value of x. In this little cartoon here, I do this, whatever that is, 10, 12 times, and I get this picture. What is the relationship between x and y? What you're doing in your head right now is symbolic regression. You're trying to go from data, and you're trying to regress back from that data, or distill that data down into an equation, a set of symbols. What is the equation for this? Have you all forgot your high school algebra?
X minus 3 squared.
Well done. X minus 3 squared. And I made things a little bit more difficult for you. I put a little bit of noise in there, right? It's not exactly x minus 3 squared, but pretty close. Okay. Assuming I'm not that smart, maybe I pick something else like y equals x. That's kind of the simplest thing that I can think of. There's the line represented by my candidate solution, y equals x. What is the fitness of this equation? The fitness is how well that line fits the data, which in this case is not very good at all. I can come up with an error measure where I take each observation, each x, I take the actual y, my observation, and I compare it to y prime, which is the predicted value of y from the equation. If x is 3, my model will produce that y equals 3, right? The vertical thin lines that you see there, the more of those thin lines you see, the worse the equation is. It's a visual representation of the amount of error. So y equals x is not very good. If y equals x existed in this population of candidate solutions, it would be a tree that just has a single node in it, x. How well do you think it would do in the population? I saw a thumbs down. Not very well, right? It's probably going to be killed off and replaced by randomly modified children of other equations that do a better job of fitting the data, like, for example, x minus 3 squared. Yeah? Question?
It's possible to like, go too far and make an equation that fits the data too well that doesn't really work for other data sets?
Absolutely, right? Is it possible to go too far? You'll notice that x minus 3 squared here is not perfect, right? There's non-zero error in this case. You could probably come up with a much more complex equation that zigs and zags and actually touches every single point exactly, and you'd get an error of 0. What is this problem of going too far? We've already seen it in a different guise. Overfitting, right? We mentioned overfitting. This is the boogeyman of machine learning and AI. It pops up in every possible machine learning algorithm you can imagine. Here is overfitting raising its scary head in genetic programming. So I mentioned that it's often very difficult to know when to stop. What's the termination criteria? So if x minus 3 appears in your population, how do you know that you should stop at this point? Thanks to your high school algebra teacher, you probably know that this is probably a good place to stop, but your genetic programming algorithm does not know. It is very difficult to know when to stop. And again, we'll come back to that later in the semester. Okay, again, this is a cartoon example. Let's look at a real data set. For those of you that have ever spent any summers in Burlington, the lake is usually beautiful, but unfortunately some of the bays in Lake Champlain during the summer suffer from cyanobacterial blooms or algal blooms. They are not good for dogs, they're not good for humans. They show up in different bays in different summers, and it's very difficult to know when and where these algal blooms will appear because we don't know what causes them. We know some of the things that cause them. For example, the more nitrogen and phosphorus that is washed into the lake from farmers' fields, because they're using nitrogen-based and phosphorus-based fertilizers, the more N and P that gets washed into the lake, that tends to cause a bloom. However, you can go and look at the actual data set. There are certain places and times in which there was relatively large amounts of N and P in that particular bay during that month of the summer, and there was no bloom. So there is not a perfect relationship between N and P, and in this case, T, which is going to be our Y value, the thing we're trying to predict. We would like to predict, given what we're seeing in terms of nitrogen and phosphorus and the temperature of this part of the lake at this time, what is the likelihood that we'll see a bloom at this place maybe a week from now? So we don't have one X anymore. We have X1, X2, X3, X4, X5. There's dozens more, and we're going to try and predict T. So as I mentioned, it turns out that N alone, P alone does not predict algal blooms. The ratio of N to P actually predicts T a little bit better than N or P alone. So if we have a population of equations, one of those equations is N, the other equation is P, the third one is N over P. N over P will kill off the other two in the population, but will eventually be killed in turn by something else that includes N over P as one term with some other terms in there. So whatever the answer is, it's a very complex relationship between these variables. It's, at least at the moment, impossible to derive that relationship by hand. Myself and Professor Epstein and some other researchers have tried to apply genetic programming to predict algal blooms in the lake. We can do pretty well, again, still not as well as we would like to be able to do. Okay, we got 3 minutes left, so let's finish with a kind of fun example here. You can go Google this and try it out yourself. There's a web application called Mona Lisa Genetic Programming. So in this case, we have a slightly different genotype and a slightly different phenotype. The fitness, as you can sort of see from this time-lapse picture here, we'd like to evolve a picture, in this case, not necessarily an equation, that approximates as closely as possible the photograph of the real painting of Mona Lisa. Okay, maybe difficult to see here. What do you think the genetic programming trees are encoding? In this case, they're not encoding equations. What do you think they're encoding?
Pixel values?
They could encode pixel values, right? That would be one way to do it. Let's assume that our photo of Mona Lisa is a 300 by 300 pixel array. We have 300 by 300. We can see that Mona Lisa is in color. That means for each pixel, we also need a red, green, and blue value. So if we have a 300 by 300 by 3 set of values, that's a lot of values, 2,700 values. It's not a very compact encoding. And as you can see from this picture, that's not quite what they're doing.
They're doing shapes.
They're doing shapes, right? You'll notice that the approximations of Mona Lisa are actually shapes. So imagine you have a tree now, and each subtree in that tree is encoding a shape. Can you be a little bit more specific? How is each subtree encoding a shape? What is that shape?
Is it like size of triangles?
It's not quite oh, actually, maybe this one it is triangles. There's different versions. I think this one is actually polygons. So within this subtree, there are specifications of a list of y values, which describe a polygon. What else is encoded in that subtree?
The colors of those polygons?
The colors of the polygons. Larger trees encode more complex polygons. We take a tree, we take all of the polygons represented by all the subtrees, lie them on top of one another. That's the genotype. The phenotype is we then compute from those layered polygons the RGB values of the 300 by 300 pixels. So the phenotype is a pixel array. The genotype is a set of polygons. And the fitness is how close the RGB values of the phenotype pixels match the actual RGB values of the picture of Mona Lisa. First of all, why would we do this? It's kind of fun. It's a great visual representation of genetic programming. It turns out that you can get a really good approximation of Mona Lisa, which with much less information than 300 by 300 by 3 RGB values. If you get a good approximation, what genetic programming is actually doing in this case is image compression. It'll give you back something that looks almost exactly like the Mona Lisa with much less information. Okay, we'll leave things there. We'll talk about physics engines on Thursday. Undergrads, get started on assignment 3. You have a quiz due tonight, and I'll see you all on Thursday.